Let's look at this other question, which is saying a 3-meter pole is suspended as shown in the diagram below. Find the weight of the pole. A 3-meter pole is suspended as shown in the diagram below. Find the weight of the pole. Okay, so this is a very, very simple question. And in order for us to be able to calculate the weight of the pole, we're supposed to apply the principle of moments. The principle of moments, like this. And one thing that you're going to notice is that they've already told us to say, or if you look at this diagram in simple terms, you can notice to say this is a suspended system, meaning it is in equilibrium. So for a system that is in equilibrium like this one, and we're applying the principle of moments, we're going to say the total clockwise moments. I'll say my clockwise moments should be equal to the total anti-clockwise moment. That's the principle that we apply when a system is suspended or in equilibrium. So these are some of the things that we're supposed to take note now before we start solving. They've said we should calculate the weight of this pole. And if you notice, they've told us to say the pole is 3 meters long. We have a pivot here, and this pivot is located 1.25 meters from one end, meaning it is not at the center of this particular pole, because if I divide my 3 over 2 to find the center of this pole, I'm going to find that my center of weight, the center of mass, the center of gravity of this pole, which is uniform in nature, is going to be acting at its midpoint, which will be 3 divided by 2, 1.5 meters like this. So I have 1.25 meters there. That means our center of mass is somewhere here at this particular point. I'll say that's where my center of mass is, or that's where our weight is acting. And there's also a particular, there's also a distance from the pivot here. There's also a distance from the pivot there to where the center of mass of the pole is. And what will be this distance? We're going to say, since we have 0.15 from here up to that end, we'll say this 0.1, or rather 1.5. We have 1.5 from this point up to that particular point, the end of this pole of 1.5 meters. So I'll say my 1.5 meters minus 1.25 meters, which means the distance from the center of mass of the pole to the pivot is equal to what? Will be equal to 1.5 meters minus 1.25 meters. This is basically going to give me 0.25 meters. This is my distance from where the pivot is located to where we are having our center of mass. As simple as that. So now that we have almost all the data that we need in order for us to be able to calculate the mass of this uniform pole, we are now going to bring our equation to say the sum of the clockwise moments should be equal to the sum of the anti-clockwise moments. Anti-clockwise moments. Moments like that. This is what we have. So what do we have as our sum of clockwise moments? You're going to notice to say we have this guy, which is acting downward like that. Then in the anti-clockwise moments, we have the weight which is acting in this particular direction, like this. Okay, so we have this force which is acting in the in the clockwise direction, whilst we have the weight of the uniform beam which is acting in the anti-clockwise direction. So for my clockwise moments, I'm going to say this is equal to force 1 multiplied by the distance 1, like this, being equal to the force 2 multiplied by the distance 2. like this. This is what we have. So the first one is the clockwise moments, which is the 625 newtons. What's the distance will be from the pivot to where the force is acting, which is basically 1.25 meters from the pivot. Then on the anti-clockwise forces, we have our weight and the distance from the pivot to where the center of mass, which is the weight in this case, also located. So I'll just plug that data in. So I have my first one, which is 622. 625 rather, multiplied by 1.25 being equal to force 2, which is the weight of the block, or the weight of the beam rather, multiplied by the distance from the pivot, which is the 0.25 meters. 0.25 meters like this. This side, if I multiply 625 and 1.25, I'm having 781.25 being equal to 0.25 W like this. I'll divide both sides by 0.25, even the other side by 0.25. I'm going to get my weight of my beam as equal to 781.25 divided by 25. So I'm getting 3,125 newtons. This is the weight of the beam. In as simple as that. So if you want, you can resolve the forces that are on this particular beam. They've given us an angle here to say this beam has been tilted to 25 degrees from the positive x-axis like that. So you can resolve your forces since you've already learned about vectors. I'm sure now you have all the knowledge needed in order for you to be able to resolve a vector. So we're going to say our weight be resolved to that direction. Even this force can be resolved to that direction. That means we're going to have our force, this force here, we also have at 25 degrees. That means we have 625 here, cos 25. Even here, we're going to have W cos 25. Like that. So we can use these forces if we want, but at the end of the day, we're going to arrive at the same answer. It's the reason I didn't bother to resolve them, because everything has been tilted to the same angle, meaning the angles can just basically cancel out each other and still remain with this same uniform equation that we have here. So it depends with what you want, but at the end of the day, you should be able to get the similar or the same answer. So we've calculated the weight of the beam since the weight or the pivot wasn't really located at the center of gravity of this particular pole. So the weight is equal to 3,125 newtons, and that marks the end of this particular question.